before we look at those, I am handing out a handout, which we will use for the second part of today's lecture. Feel free to take a look at it. Okay, so a couple of things. First things first, Alex. If you've looked at Alex, there are, I think, 5 objectives. When I walk back up to my office, it's going to go from 5 to 1. Just one objective is due on Monday. We're going to talk about 2 things today. Hess's law, the way Alex is going to ask you to solve it, is not at all consistent with what we do in here. Therefore, there are no objectives on that, because that doesn't work for anyone, right? So Hess's law will be on mini exam 4 and probably the final. I recommend that you either use the book, you can Google Hess's law problems on the worksheet. You will need to do some additional practice other than what is presented in class, and Alex cannot facilitate that for you. The second topic today is heats of formation, which is this graphic. Well, I have most of our attention. So in this is out of the textbook. It will help you with today's lecture. So the thing is, this is like a really abbreviated list, because that's how tables work. If you own the textbook, like all 2 of you, I told you not to buy it, so like I'd be shocked if all of you were like, yep, I own that. At the back, there's something called Appendix C. You can find all of the delta H naught F values in there. The other place that you can find them is on Alex. If you click the data values, it looks like the little like bar graph thing, like it looks on here. I'm very proud of my emoji usage. Then you'll scroll down, and you're looking for something called Thermodynamic Properties. Click that. It's going to pop out a table. There are, it's a row of compounds and then 3 values. Make sure that you use the ones in the first column. The other 2 columns are irrelevant for this semester. There are other values in here. If you're like, I hate Alex and I don't want to use it, you can also Google heats of formation tables. There are a variety of free resources. They're just like not bite-sized information. It's like a tome of like thousands of values, which may be overwhelming. It's overwhelming to me, so like, there you go. So there's that. Next Wednesday, your Chem and Life 2 is due. Please make a point to make them legal. If you do something illegal, I will have to report you it's like a whole thing. I serve on the conduct board. I'm well aware of what student conduct allows. If you do something illegal, I have to tell on you. It's not fun. I don't want to be there. That is due next week. It is 300 words, a single PDF. As a reminder, here is what it tells you that you need. If you only wrote 100 words, you get less credit than 300. I'm not asking for a deep dive analysis of something. I'm asking for what you saw and not how it made you feel, but like, how did you experience this? If you're having issues, please send me an email from Docs Hours. It's due next Wednesday at the start of class. You may or may not be aware, but I only brought my small tote with me today. Your exams are not yet graded. I have started grading. I graded for like an hour today, so I'm both happy and like disheartened. It seems like some of you did really well. It seems like there are some of you who have a hard time or you skipped around, and I only graded like 1 through 6. So like, you might have gotten the rest of it all correct, and I only saw the beginning, but they will be returned on Monday, in case you are anxiously awaiting them, and I don't want to like not provide that information to you. Questions about anything? Yeah.
So besides Hess's law, will there be anything outside of like chapter 6 that we need to know of for the mini exam 4 for next week?
The mini exam 4 is, it's a great question, and I should have looked at a calendar, but it's not next week. It's November 1st. So I was like, all I know is it's not next week. So our mini exams in the first half of the semester were on Wednesday. They're going to move to Mondays. So hopefully that will help with some of the, I'd like more time to learn the material. So it is Monday the 1st, and it will cover today and next week. So there are other topics, whatever we talk about out of chapter 6 next week. That announcement is more, I always want to make a point when Alex is not going to function as a viable review tool, because it is a great tool, except for Hess's law, because it basically asks you to do a calculation that I've never once done in my professional career in that way. So I think it would be silly to ask you to do that as well. So today you will have unobjective, like 1. But if you look at it right now, because you're sitting in here, it hasn't been done because I am not in my office. But it will happen as soon as, like, I go upstairs, I move this video to YouTube, and I'm going to fix the Alex stuff. Just so we're all aware of, like, my timeline in life. Other questions? Sweet. So, today, we're going to start with a brief reminder. So, probably like 2 weeks ago, many moons ago, I don't know how long ago it was, I don't know about dates anymore, I think it was before mini exam 3, in that lecture, when we talked about the calculation of delta H. So delta H is enthalpy, and today we're going to focus on that. But it's really important to note that enthalpy is an extensive property, so it is proportional. If it requires 5 amounts of energy, 5 kilojoules to make 5 cookies, we know that to make 25 cookies, it would I can't do that kind of math. Let's reboot that question. If it takes 5 kilojoules of energy to make 1 cookie, in order to make 10 cookies, you need 50 kilojoules. It's proportional. So the other thing is that the enthalpy change for a reaction is equal in magnitude, but opposite in sign. So the amount of energy that it takes me to go this direction, technically for me to go back, it feels like it's the same amount of energy, which it is, because that's how we all think about life. But if you were to write an equation, it would be negative. So if this was positive, it's negative, but the same number of steps. And so more often than not, in Gen Chem 1, states are somewhat irrelevant, except for like chapter 4 when it's like, what is the precipitate? In this case, the states will always be provided to you. So I'm not asking you to say like, what is this, a gas? Is it a liquid? Is it whatever? I'm asking you to make sure that when you read values off of the table, you use the right state, or when we look at reactions, we use the right states. Basically, all I'm trying to highlight is when we look at Hess's law, make sure you look at the whole part of the problem, not just the coefficients and the substrates. Because the numbers at the states could be important. So, we're going past all this to Hess's law. So Hess's law is probably one of my favorite topics. And students, once you get the hang of it, really like it. So, at the risk of making myself sound like someone who stays home and does illusory things, puzzles and Sudokus are like my jam. I liked puzzles before the pandemic when everyone stayed home and like did puzzles for 3 weeks. So it's about my life, not about yours. But the thing with Hess's law and puzzles, it is impossible for you to look at a 1,000-piece puzzle and automatically know where all the pieces go, right? I tend to look at one piece at a time, or I sort them. If it's making a red bird, like I pull all the red ones together and I'm like, oh, look, these go together. But it's really hard to look at 1,000 pieces and be like, these. Maybe you get lucky. There's always that one piece. But for the rest of them, it requires you to sort either pieces of the puzzles independently or one piece at a time. So when we look at a Hess's law problem, it's important to note we want to make sure that we don't get overwhelmed, because the number one thing students do is panic that they don't know what to do. That's true on all topics. In this case, we're going to talk about how to handle our panic in order to be able to move forward. So Hess's law, when I find my notes. Hess's law states if a reaction is carried out in a series of steps, delta H reaction is equal to the sum of the parts. So basically, if we want to know if A goes to D, delta H reaction equals question mark. So we don't know that. But what we do know is that A goes to B, delta H equals plus 12 kilojoules. If we know that C goes to B, delta H is equal to negative 15 kilojoules, and D goes to C, this delta H is equal to negative 17 kilojoules. So we have these three steps, and we want to be able to calculate delta H reaction. The reality is we can make a series of statements. So we know that A goes to D is what we care about. But we also know all of this information. For ease of tracking, I'd like to label my equations. 1, 2, 3. You can name them anything you want. Circles, stars, potatoes, 1 dot, 2 dot, doesn't matter. Red, blue, green. But this allows me, when I start to do work with them, for you to be able to follow, like, oh, I know where she's going. So the reality is, when we look at this, there's two ways you can tackle each one. For each equation, look at it alone. Don't look at all three, just one. For this one, we want to ask ourselves, what does it look like for this equation? A is in the right place. We're going to use number 1 as is. Oh man, I'm out of space. Go over here. So we're going to use 1 as is, which says A goes to B, delta H, 1 equals plus 12. So C doesn't match this at all, or B, no. Number 2 doesn't match this, so we're going to skip that. For number 3, D goes to C. Well, D needs to be a product, so we can flip this. When we flip the equation, we just need to change the sign on delta H. So we're going to flip number 3 and know that C goes to D. So delta H3 is now equal to plus 17 kilojoules. So we can sum these up, but that's A plus C goes to B plus D. And that doesn't look it looks somewhat like what we wanted, right? But we have these, if I write the right letters, we're in a better place. We have A plus C goes to B plus D, but I only want A goes to D. So, I'm gonna erase that. Well, we have this equation 2. because it's the sum of its parts, we can use additional equations to basically get rid of excess junk. Excess junk is quite strong. We'll just say participants that we don't see at the final equation. So for equation 2, we need to flip that one as well, because we need to get the b and the c to cancel out, and as it's written, we will end up with a plus 2c, 2 b's, 1 d. So we're going to flip number 2, and that's going to give me b goes to c, and delta H2 is now equal to plus 15 kilojoules. So now we can sum this up. So we get A plus C plus B gives me B plus D plus C. If we remember our spectator ions, anything we see on both sides can go. So we see a B on both sides, and we see a C on both sides. So our final equation is A goes to D, and we were able to determine that the delta H reaction, 14, I think it's 44, but I totally made up this on the fly, so if that's not the right number, someone let me know. But I'm relative, yeah. Yes, I'm confident. Might still be wrong, but I'm confidently wrong. So the things that we need to know from this that are really important before we look at our next example. 1, all of this information will be provided to you. It will also come with states, just so we're all aware. So sometimes you will get extra equations, but you will always have enough. You want to make sure that you check the states, and there were none in here, so there was no examples of that, but the next one talks about it. This is basically the type of information that you want. So because it usually comes up in here, how much of this work do we have to show? There's a whole range of work. You can't just write down delta H and then a value if you would like full credit. You could write down just this information. You might not have to do all this, but you do need some way for me to see that you use Hess's law for the equation and something that looks like this. Questions before we work our first, I don't want to call it real example, but like one that has chemicals in it. Yeah?
With 15 and 17 kilojoules, do they become positive because you like manipulated them basically?
Because you flip it. So when in a reaction, if it takes 15 kilojoules to go that way, it is negative 15 kilojoules to get back. So basically what that means is, in order to go from A to B, you have to put in 12 kilojoules of energy. To go from B to A, it should put out 12 kilojoules of energy, which is what the negative means. It means it's leaving the system in that case. Good question. Other questions? Yeah?
We're going to be, so we're going to be given those values we wanted to determine.
It'll look, so we're going to do this example, but it could look like this. So we're going to go back to the other one, but I want to make sure that so it would be that it would give you an equation, and it'll say like calculate delta H for this unknown equation using the equations at the bottom. This one just doesn't really have a lot going on, so I want to make sure. There would be everything you need, just maybe more, because that's how I roll. So let's look at this first example. Actually, while you look at it, I'm going to erase the board so that we can write on the board. So in this one it says, calculate delta H reaction for basically the combustion of methane. Now, all equations will be given to you in a balanced form. You might have to multiply everything by a value or use it as is, as well as the states. So using the equations at the bottom, when we look at the first equation, so this one, it looks a lot like the equation we want to know about, right? What is the only difference? Yeah, the water's in the wrong state. So we need to be able to figure out the change in enthalpy when we convert the gaseous water to liquid water. So in this case, we're going to use one as is. So it'll be CH4 gas plus 2O2 gas gives you CO2 gas plus 2H2O gas. And we know that this delta H is equal to negative 802 kilojoules. Not a decimal point. So the second equation, do we need to modify that in any way in order to use it? No. So we don't necessarily want to flip it because we want to make sure that what is in the top equation is on the right place. So we would like the liquid water to be on the right side, on the product side. So we're going to add the H2H2O liquid plus 2H2O gas. So from here, oops, this delta H is negative 88 kilojoules. So we're going to add these up. So we have CH4 gas plus 2O2 gas plus 2H2O, also gas, CO2 gas plus 2H2O gas plus 2H2O liquid. And if your arms are tired, that's normal. So from here, we can cancel out anything we see on both sides, which is just the 2H2O gas. So we can then sum up our equation, CH4 gas plus 2O2 gas goes to CO2 gas plus 2H2O liquid. This looks like what we wanted. You have reached your destination. That's all it's asking you to do. So now we're going to add up our two delta H's to determine that delta H reaction is equal to negative 890 kilojoules. What questions do we have about this first example? Yes?
I'm a little confused on how is it again that we're supposed to know if we should leave the liquid and the gas in their positions?
It's a good question. So the question is, how do we know if they're in the right position, essentially? So when we look at the second equation, we have 2H2O gas goes to 2H2O liquid. The way you know if it's in the right arrangement or if it needs to be multiplied is by comparing it to the top equation, the original one. So in that case, we know that we need 2H2O of the liquid, and we need it to be a product. In theory, if you use all of the equations and make the, I don't want to call it the meaty part, but the majority of the equation match some part of the top equation, it should all shake out. Should is the optimum word there, just to be clear. Sometimes some weird stuff happens. Are we ready for our next example? Feels like a few of us are. Any more questions before we try the next? So in this case, we'd like to calculate delta H reaction for carbon solid plus half O2 gas goes to carbon monoxide. Using carbon solid plus oxygen gas gives you CO2, and carbon monoxide plus half O2 goes to carbon dioxide. Right? Yeah. Do you want to try this, or shall I work it? Let me see. think a lot of, I should just do this. It's okay. There's nothing wrong with that answer. I just wanted to know. It's okay. I like working these problems. I want to give you an opportunity. If you were just sitting there waiting for everyone, you know. Okay. So I'm going to annotate mine as equation 1 and 2. Literally the first one and the second one, that's how I'm numbering mine. You can number them however you want. So for the first one, when I look at that equation, if I look on the product side, it's CO2. CO2 is nowhere in our top equation. But carbon and oxygen both need to be reactants. So we can leave that equation alone as it is. So we're going to use 1 as is. So we have carbon solid plus O2 gas goes to CO2 gas. And that delta H reaction is negative 393.5 kilojoules. Now, equation 2. There's 2 reasons that we can decide to flip this. Option 1, the carbon monoxide is a reactant and we need it to be a product. And we need it to be a product because that's where it is in the top reaction. Alternatively, you could have also decided to flip it because CO2, you need to get rid of that. And the only way to get rid of something is for it to be on both sides of the arrow. So we're going to flip number 2. You can think about this as basically just a rotational point. Everything on one side goes to the other, full switch, and the sign is going to flip from negative to positive. So we're going to have CO2 gas goes to CO gas plus 1/2 O2 gas. And now delta H is positive 283.0 kilojoules. You do not have to use the positive signs. I do it so that I know that I haven't lost a negative. That's all. That's why they're there. So now we're going to add these up, make sure we got it right. So we have carbon solid plus O2 gas plus CO2 gas gives me CO2 gas plus CO gas plus 1/2 O2 gas. So now we got to get rid of anything on both sides. So the CO2 gas is relatively obvious that we see it on both sides. So the carbon looks good, the carbon monoxide looks good, but these oxygen is unbalanced. Anything you see on both sides can be canceled. You could rewrite this as 1/2 O2 gas plus 1/2 O2 gas. And that would make it a little easier for you to see that we're just going to remove 1/2 mole from each side, which gives us carbon solid plus 1/2 O2 goes to carbon monoxide gas. So our delta H is going to be the sum of these two values, and that is negative 110.5 kilojoules. So what questions do we have about this example? Oh, sorry, let me move out. Are we feeling, yeah.
I think what I just am like really confused on is like when you like draw the line, you put the equation, but then you just like add everything below that.
Yes. So I add everything to make sure that you get the final equation. So in some of the next ones, we'll have to do more than one thing, not just flipping. We're going to start multiplying things with you. We're going to start multiplying the equations. And so when you do that, it's really important to make sure that you end up with what you were shooting for. as opposed to just determining some other calculation.
So how exactly do you make 2 halves from the regular L2?
Follow my logic here. If we have 1 pie, obviously I need to eat more. If you cut it in half, you have 2 half pies, right? So we know that 1 mole of oxygen is 1/2 plus 1/2. So I did this to give you a visualization, which I'm sure you can't see because of the podium, so I'll move that in just a second. Basically, we need to remove 1/2 from both sides. And we can do that because there's a hole on this side. And you could have. The alternative would have been to just say like minus 1/2 and minus 1/2. But I find that this visualization gives you, once you think about it a little longer.
Yeah.
Any other questions? Yeah.
So basically, your end product is supposed to be, what you're calculating for.
Yes. If you do this correctly, which is our goal here, what you get at the end should be that. And once you do that, you can basically sum up all of the rest of your delta H's to give you the delta H of reaction using the other reaction parts. Other questions? Do we want to try this one alone? I'm seeing enough nods. Let's go for it. As always, if you get stuck or have questions, let me know. I will happily bounce around to answer questions. Yes. So in that case, you want to make sure that you're looking at each one independently, because if you try to do everything out of this, told you that you had to run 1 mile, that took, I don't know, however 1 mile. Technically, if you were to be like sucked off, it wouldn't be inverse of that amount of energy.
The majority of the questions will be about chapter 2.
Well, so it'll be today, and then however long these numbers that you get done.
Okay. So it includes all the stuff that we have that we're doing right now, is what you're saying.
So it always is a lecture.
Okay, never like the chapters. Okay.
Sorry. It's basically from, so you just start with that my chapter 5,
And
what
then
we did, and then
chapter 6.
we'll finish all of chapter 6 into lecture. We have a little. Don't, whatever is left of 6, we'll watch at the beginning of that lecture.
Okay.
So, the 6 objectives will be out. Because if you go in there, there are chapter 6 objectives. But they will basically move back. And I will get what I can do with them. So usually on Wednesday, I adjust for where I thought we would go. So I made them based on. I don't know what happened. We're not on Wednesday. All right, how many? Well, let's ask a different question. Who would like to share their numerical value? Answer. I feel like I saw half of you do the question. Everyone I looked at did it right. Okay, no takers.
Is it 6:20?
I got 226.8. Not really sure where your numbers went. So for the first equation, when we look at that, it's got a lot of stuff. Only a single value can be found in our, I guess we could call it the prompt. So in this case, the C2H2 needs to become a product. In order to do that, we're going to flip that equation. So we're going to flip one. And so we're going to get 2CO2 gas plus H2O liquid gets to C2H2 gas plus 5 halves O2 gas. And our delta H goes from negative 1299.6 to positive 1299.6 kilojoules. For the second one, what do we need to do to that equation? We need to multiply by 2. So we need to do that because in our prompt equation, we have 2 moles of carbon solid. So we're going to multiply everything by 2. So we're going to mult number 2 by 2. So we have 2 carbon solid plus 2 O2 gas goes to 2 CO2 gas. So our delta H equals 2 times negative 393.5, which gives us negative 787.0 kilojoules. So for our next equation, we're going to use that as is, because the hydrogen gas is in the same state and coefficient. So we're going to take our H2 gas plus half O2. And that gives us H2O liquid. And our delta H here is negative 285.8 kilojoules. Now we're going to total it all up to make sure we got the right answer. So we have 2 CO2 gas plus H2O liquid plus 2 carbon solid plus 2 O2 gas plus H2 gas plus half O2 gas. All of this gives us C2H2 gas plus 5 halves of O2 gas plus 2 CO2, still gas, plus H2O liquid. So now I can find my red marker. We can cancel out anything we see on both sides. CO2 gas, H2O liquid. So when we look at this, we have 2 carbon solid plus H2 gas, which is what we know. And we have 2.5 moles of O2 on the left. And we have 5 halves, which is 2.5 on the right. So we can cancel all of those to give us the equation we wanted of 2 carbon solid plus H2 gas gives us C2H2 gas. So delta H is 226.8. We're positive 226.8 kilojoules. Questions? Did you figure out what happened?
Yeah, I didn't multiply the numbers now, but number 2.
Oh, you forgot to multiply delta H by 2. Whoop. That happened. Other questions about Hess's law? Yeah.
So our product, basically our product is supposed to look like the beginning equation that calculate delta H. They should look the same. And then you're going to feel like you did it right.
Yes. So what could happen, and didn't happen in any of these, is let's say you forgot to multiply this by 2. You would have ended up in a place where you'd have only had 1 carbon, and you would not have enough oxygen. So basically, you would be missing carbon and oxygen. Different parts for different places. Good question. Any other questions? So for the next half hour-ish, we're going to talk about probably the easiest way to calculate delta H. So Hess's law is based inherently upon the heats of formation. The heats of formation is basically the enthalpy required to make something. So there are many, many, many different thermodynamic tables. We are going to talk about heats of formation. The heat of formation is the ability or the energy / enthalpy required to form a substance from its parts. A good example of that is this equation here. So it is the energy created, or the energy required to make 1 mole. So this is why we're starting to see some non-whole coefficients. So it says half, well, it did say half O2. I got a little excited with the eraser. So we have H2 plus half of O2 gives you 1 mole of H2O. In this case, it tells us, so we know that delta H reaction is negative 285. This delta H reaction is the same as delta H of negative 285.8 kilojoules. So it requires, or in this case, negative 285.8 kilojoules of energy are released in order to form 1 mole of liquid water from half mole of oxygen and a whole mole of hydrogen. So let's talk about these values. Delta H, enthalpy, we know him, or her, them. F is formation. There are other types of tables. You could calculate the delta H of combustion or other things. And then this little degree symbol is actually the word not, N-A-U-G-H-T. It is impossible for me in my mildly southern accent for it to sound like anything other than the word N-O-T or K-N-O-T. They all are the same, man. So delta H, not F, basically means the heat of formation, and this degree symbol means that it's at standard temperature and pressure. The reality is most, if not all, of our chemical reactions are conducted at at temperatures other than 298 Kelvin. Turns out that room temperature in this building is not that. It's close. So in Chem 2 and in physical chemistry, if you're a chem major and hang around for that, we'll talk about how to adjust these numbers. For Gen Chem 1, we only live in the ideal land. It's a great place. Everything works perfectly, and we are only going to be at 1 atmosphere and 298 Kelvin. So delta H naught F is the change in enthalpy for the reaction that forms 1 mole of a compound from its elements in their standard state. Standard state is basically how you find them in the periodic table. We know that a handful of them are diatomics. Anything that's a metal really only comes as like a metal, like copper, cobalt. They just come as like copper solid. There are some of them that are weird. So when you look at the table, you'll see that carbon comes in many, many, many different forms. From graphite to graphene to diamond to liquid carbon. All of those require different amounts of energies. So this is the standard enthalpy table. This is the handout I gave you, so that if you didn't print the slide, you can do the calculations coming up. When you look at this, it tends to have the substance, the formula, delta H naught F is the number. Make sure that you bring the sign, whether it's positive or negative, with you into your calculations. If you do the worksheet, right, so I make the worksheets on Canvas, not everything you need is in this table. You might have to either use the one out of the book or the one in Alex. The one in Alex has a lot more values. It's important to note, I will give you some portion of this table on the mini exam. So it would literally read like the question and then a table right under it. You won't have to go very far for it. It'll be right there. Just want you all to know that. So these are the standard values. So what does this really mean and why do we care? So the reality is we can calculate delta H reactions. We learned how to do that with calorimetry. We just saw how to do it with Hess's law. And we're going to use the heat subformation. The reality is, it's asking about how much energy does it take to make something. If you go to Publix or Winn-Dixie or wherever it is you buy groceries, and you buy break and bake cookies, you go home, you turn the oven on, get the sheet pan out, put cookies on it, make cookies. Energy input, almost none. If instead you're like, I'm going to weigh out flour or measure, depending on how accurate you want to be, break eggs, stir the stuff together, that requires a lot more energy, right? So the reality is the energy required for the reaction is dependent upon the method, the states of your ingredients, as well as how many different ingredients there are. So we know that delta H can be thought about as H final minus H initial. In terms of a reaction, that is H products minus H reactants. If we know, based on Hess's law, that a reaction can be calculated by the sum of its parts, we could calculate delta H not F of the reaction, or delta H reaction, let's write that a different way, is equal to the sum of delta H not F of the products minus the sum of delta H not F of the reactants. So as we start to look at the delta H not F values that come out of a table, you could write equations, basically all of the elements in their elemental states going forward. Most of the time we're going to read stuff out of the table. The things that are complicated are things that come in their elemental state. Few catches here. It's got to be how you find it in nature. So if it is a lone metal, like cobalt solid, the heat of formation is 0. The heat of formation is how much energy it takes to make something. If you can just find it-ish in nature, it doesn't require any energy. It might require energy to purify it, but it requires no energy to isolate it. So in that case, it's 0. Native states are equal to 0. These are the same ones for oxidation numbers where they're 0, like metals or diatomic gases. It has to be a single element, though. And so then it also matters that they're states. So it requires different energy to make gaseous water versus liquid water. Most of this is going to come out of a table. So we've talked about this. Oh, the other part is we can multiply delta H naught F by stoichiometric values since they are per mole. So if it requires 5 kilojoules of energy to make 1 mole, if we need 10 moles, we would need 50. So let's look at an example. So this equation is good, but what does that really mean? If we want to calculate delta H reaction for the combustion of liquid benzene, we are given an equation. In this case, we know that delta H reaction is going to be equal to the sum of the delta H not F of the reactant, note the products, minus delta H, the sum of delta H not F of the reactants. So now you just write it out for each one in the equation. So we know that it equals 6 times delta H not F of CO2 plus 3 times delta H not F of H2O minus delta H not F of benzene, C6H6, plus 15 halves, delta H not F of O2. Now, we look at the table I gave you, and we start to plug in values. So we see that it's equal to 6 times negative 393.5 plus 3 times negative 285.8 minus 1 times 49 plus 15 halves. What is the heat of formation of oxygen? Oh, sorry. There's a sharpener there. Sorry, internet people. That was a weird noise. Is oxygen in its native state? Yes. So the heat of formation is 0. So now we just start to plug values into our calculator. If you do that, you should get negative 3,267 kilojoules. A couple of tips. Y'all, math is hard. So we all know this. This is not new for Gen Chem 1. One of the things you'll notice is that I'm using brackets. Make sure that you sum if there's more than one value in here together so that you don't lose whether it's a negative or a positive. So a minus a negative number turns positive. If we remember back to, I don't know, math, when we took math before in our lives. And make sure that your negative signs, if you have them, they need to come with you. So this is, in fact, a subtraction problem in this case. We're going to look at some examples where, like, the math reminder will make more sense to literally the next one. Questions about this example? Fantastic. So, this one is a new flavor. I have seen you all semester. I know, this reading the table, plugging in values, is a skill that you have. We have looked at that, and we've done that a lot. So let's look at the other ways that we could use the delta H naught F, because you could calculate delta H reaction, or if you're given that, you could solve it for one of these other values. So, in this question, it says, the standard enthalpy change, so delta H reaction, for the reaction or the decomposition of calcium carbonate is 178.1 kilojoules. Using the table, calculate the heat of formation for calcium carbonate. I'm well aware that if you look at that table, the value is in there. Obviously, on an exam, you will not have that whole table. So we're going to do this like you don't already know the answer, but we'll know if we get the right answer. Just so that we're aware. So we know that calcium carbonate solid decomposes into calcium oxide plus CO2 gas. We know that delta H reaction equals 178.1 kilojoules. So we're asked to determine what the heat of formation for calcium carbonate is. So we know the delta H reaction is equal to the sum, or it's equal to the delta H naught F of calcium oxide plus delta H naught F of CO2 gas minus delta H naught F of calcium carbonate. So ordinarily, we would use the values from the table, plug it in here, and get 178.1. But I'm asking you to find this value for a known reaction. So now we can start to plug that in. So we have 178.1 kilojoules equals negative 635.5 kilojoules plus negative 393.5 kilojoules minus, delta H naught F, calcium carbonate. When we start plugging this into our calculator, we end up with 1207.1 kilojoules equals negative delta H naught F, calcium carbonate. So you might be thinking, I wonder where that negative sign came from. It turns out that a subtraction sign and a negative sign are the same. Mathematically things. So in this case, in order to solve for the answer, you have to divide by -1. So delta H naught F is calcium carbonate equals negative 1207.1 kilojoules. Yeah. So if you take 178.1 and then you add these together, you should get, I have no idea. Hold on. $635.5. So you get negative 1,029 kilojoules. In order to get it on the other side, you add 1029 to both sides. So this is 178.1 plus 129 kilojoules. And when you add those two together, you get positive 1207.1. But this negative sign, because we are supposed to subtract that H naught F value, this means that in order to find the delta H, you have to put the negative sign on the other side. It's a good question. It's a hard, I don't know, I think math is hard. Let's just all be honest. What other questions do you have about this example? This example is very similar to this one. I'm going to give you 5 or so minutes to solve that. I have an additional Hess's law example that we will not have time for, but I will write it on the board over on the side. That way you can take it home with you to give it a go. Oops, that's like a weird box. Don't forget, if you get stuck on part A, you can just do part B. Yeah. This came out of the table. Yes. So all of those values would come out of that table. The appendix on Alex, or on like an exam, it would be like this, and then underneath it there would be like a table with data in there. Yes. Is H2 in its standard state? Okay. Oh yeah. Well, isn't it asking where the delta H naught F of copper oxide? You gave me a price there for a second. I was like, it's not. How could anyone do this? But that's the answer they were looking for.
No, but it can only be half an hour. So it would be six.
Yeah. Okay, you're getting there, I think. You're doing things. Those are good. How's it coming? In between, that's what I'm seeing. Okay. Feel free to keep working. I am going to start solving. That way we get out on time. So we know, just similar to the previous one, the delta H reaction equals the sum of delta H, not F, for the products, minus the sum of delta H, not F, for the reactants. So we know that in this case, the reaction is negative 129.7 kilojoules, and that equals the delta H, not F, for copper oxide, plus the delta H, not F. Nope, that's copper solid, sorry. Plus delta H of H2O liquid minus delta H, not F, of copper oxide, plus delta H, not F, of H2. So when we start to look at this, it's really easy to get bogged down and kind of stressed out. So the number one thing students do is they look at the table and they panic when they can't find something. Fair. This is the first time we've seen it. If it's not in the table, more than likely it's one that we should know, or you're looking for them. When an element is alone, O2, H2, Cl2, copper, sodium, in its native state, so copper metal, the heat of formation is 0. Hydrogen gas, the heat of formation is also 0. So we take our negative 129.7 kilojoules, and that equals negative 285.8 minus delta H dot F of copper oxide plus 0. So delta H, not F, of copper oxide is equal to negative 156.1 kilojoules. So what questions do we have about the first part? Yeah.
Why is it that when we switched it, the delta H didn't become positive? So they started with CuO, and then down here you put Cu plus H2O.
So this one?
Yeah, so here you have Cu plus H2O, but in the problem we started with CuO.
So it's products minus reactants.
So you wouldn't change the.
So the equation stays the way that it is. But you're just solving for the heat of formation for just one of those values. So for part B, the enthalpy change is proportional to what we see in the equation. So we know that delta H of the reaction is negative 129.7 kilojoules per 1 mole of copper. And this comes from the equation. So if it had been 5 moles, it would be per 5 moles. If it was 3,000 moles, it would be divided by 3,000. And then we're going to multiply that by the number of moles that we have. So in order to figure that out, we'll take 3.203 grams of copper, divide by the 63.55 grams in 1 mole of copper, and all together now this gives you negative 6.537 kilojoules. Because there is not nearly enough time ever in our labs, over here on the right side of the board is a Hess's law example. please give it a go. If you work it, you can send me an email with a screenshot of your work. I'm happy to look at it. I'll be here for a few minutes if you've worked it and would like to talk about it. Any questions? Excellent. Well, I will see you guys all next Monday. Have a fantastic weekend. We will start chapter 6 on Monday.